introduce you to my new home-built Rose engine. The design brief I gave myself was that it should be light enough to be easily portable for demonstrations. It should be driven by a stepper motor and have electronics that are freely available on the internet. So at the headstock end, virtually everything is built out of reclaimed floorboard and kitchen worktop from a kitchen that we changed. So the rocking headstock sits on two roller skate bearings with an M8 rod between them. The stepper motor is built inside of the headstock structure, and on top of which sits two 1-inch bearings with a brass shaft with the chuck on one end and a clutch mechanism and rosettes on the other. I designed it to take only one rosette at a time. The rubbers sit on brass rods, as pretty much you will have seen in my other Rose engines. The stepper motor is held in place by friction. There's just two bolts, one on each corner of the stepper motor, and it's sandwiched between the uprights of the headstock structure. This allows me to slide it up and down to tension the belt. The rosette mechanisms are attached using a threaded bolt and a clamping mechanism. The drive shaft has a hole drilled and tapped to take an M6 lever action bolt, and the rosettes are fitted over the top with spacers that is now clamped tight, and the rosette is firmly clamped to the aluminium backplate. A little box in the front is where I can put rubbers and Spirograph wheels temporarily while I fiddle about, and spare rosettes can fit on the end so that they're available when I need them. Spare rubbers also sit on the overlong bolts that hold the structure together. The structure on the right here is a brake which allows the rosettes to be braked, and with the clutch released it becomes possible to phase. They hold the rosettes in a very rigid place, very rigid way, and the electronics, which I'll go through in a bit, allow you to rotate by as small as 1 degree at a time, and with a 1:3 ratio on the belt, the small pulley to large pulley, in effect you can phase right down to 1/3 of a degree, which is probably ridiculously accurate and entirely unnecessary. On the top there's just a little hole there where I keep the chuck key, so that everything is handy. On the tailstock end we have the electronics, the power supplies embedded in underneath a XY mechanism. The X travel on the base is made out of 3D printer parts, and the whole will slide, so I can move it. There's a whole huge range of movement. Once you've slid it to the position you want, I then tighten down this nut here, and that locks the mechanism against the T-bars that it sits on. On top of that sits a very cheap £28 XY compound table, not especially high quality but just about good enough for the job. And the laser in this case is mounted on a cheap tool post. I can also swap that out for a flexible drive. It's also mounted on the same tool post, and that's driven by a Dremel, which is a bit noisy, but it actually does the job. Also, there's a small light there so that everything is illuminated for me. The spring is adjustable using a adjustable cable tie down here, so I can adjust the tension on the spring, and that sits on a little wooden bar which also is used to store, if I get this out of the way, frequently used Allen keys. That's the electronics for the laser, and this setup is primarily designed for use as a laser etching machine rather than for engraving. I do not yet have a proper universal cutting mechanism, although I suspect that I will do that sooner rather than later. The electronics are fascinating. They came with absolutely no instructions at all, but simply put, hold and press this button and it comes up with a P number, and there are 7 different programs: P2, P3, P4, P5, P6, P7, and then back to P1. In effect, P2 drives the motor continuously. If you press this button, it goes one way, and if you press this button, it goes the opposite way. And the top button controls the speed. On P3, the machine will drive the mechanism in the number of degrees stated on the lower display. So pushing this button goes 45 degrees in one direction, and in this button 45 degrees in the other. What you of course has to remember is, though it's 45 degrees on the direct drive, but you have to multiply that by 3 in order to get the correct number of degrees that the wheel will actually turn. There, in order to get 22 degrees on the chuck, you'll have to multiply it by 3 and put it up to 66. .66 degrees there will actually deliver 22 degrees at the chuck. The way the brake works is quite simple. Tighten it down on the tool rest. Tighten it down on the rosette. Release the clutch. and then press, I think we've got it set for 22 degrees. So the inner wheel rotates 22 degrees to, well, it's about 7 degrees. So if you're phasing it by 7 degrees, that's near enough. Tighten the clutch. Release the brake, and you have in effect phased by your piece of work. To odd P2 and set it going with a simple sine wave rosette. Probably needs to go a little bit slower than that, and we will advance the pen. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 peaks on the sine wave, which makes that one peak every 30 degrees. So in order to phase this by 50%, we need to get the control to move it. Now that is set for 45 degrees. We'll apply the brake. Release the clutch and press the button. That looks to me to be about right. Tighten the clutch. And apply the pen. And there you have a phased 12-point sine wave. And now we'll set it up to do a Pat Miller type spirograph design. First of all, we take off the spacers on the existing rosette. This is the big spirograph wheel sandwiched between two pieces of wood. Wide. Don't think it needs another spacer. This is the rubber. It does need another spacer to make room for the rubber. Rubber now in place. Remove the wedge, fine tune the positioning a little bit, and it's pretty much ready to go. Spirograph wheels are 3D printed from files on Thingiverse. I don't think they're quite as accurate or as reliable as the real thing, so I think I will go back to purchasing a new Spirograph set. They cost about £18, but I do feel the cogwheels work more reliably than my 3D printed ones. I do find the pen tips don't last terribly well with this, but it does give you an idea of what your designs might look like before you start applying them to a piece of wood. This is what the Spirograph mechanism actually looks like. Big wheel is sandwiched between two pieces of wood to keep the smaller wheel in place. The other thing that I forgot to tell you about is my built-in eye protection. When using the laser, saves having to use glasses. I just cover up the focus of the laser. Another point worth noting is that I've experimented with a couple of different stepper motors, and I find you need at least 3.0 nanometers holding power. This particular stepper motor costs £36 from Amazon, so not hugely expensive, but it's worth the extra to get one with bigger holding power. I found 2.7 nanometers holding power wasn't big enough. give it a go. Very slight loss of accuracy with the pen because it tends to just slop about a bit with the pen holder, despite wrapping the pen with some tape just to keep it close. And then the accuracy is exceptionally nice to keep it. So there's the finished design. As you see, there's one stroke which is not quite accurate enough, and a little blip on the outer rim. I'm not quite sure what that is, but I'm fairly confident that will go away when I start using proper Spirograph wheels rather than the 3D printed ones. I hope you found this interesting. For those of you that like to see the laser at work, here's the same Spirograph pattern being drawn by a laser at 5 times normal speed. And here's the same pattern being drawn at a much smaller diameter in the center of the first pattern.